So the bat population in a certain Midwestern county was 350,000 in 2012, and the observed doubling time is 25 years. For part A, we're supposed to find an exponential model based on the doubling time, and the years are since or after 2012, which means t equals 0 is 2012. So that's my starting amount. That just ends up being, I guess, a plug and chug. So n of t is equal to, this is my starting amount, 350,000 bats, and it's doubling, they told us, every 25 years. So this is my a value, and this was my n naught value. So t divided by 25, because it's doubling every 25 years. That's part A. Give the model in terms of the doubling time. Part B requires a little bit more work because they want us to find an exponential model of this form, meaning in terms of its relative growth for that population. So you can have models in terms of different types of growth, and all of them will predict future values if you need them. So for the population, if I try to do that, I'll start off with n of t equals, I know the initial population was 350,000, e raised to the RT, I don't know what r is because in this problem they did not tell me what the relative growth rate is. They just told me that it doubles in 25 years. So I don't know r, I'm just going to leave it as is and try to find it with the information I have. Now there's different ways to do it, but we're just going to logically think through this and be like, okay, well, they gave me the doubling time, so we know 350,000 doubles to, if I multiply that by 2, I get 700,000. And that happens in 25 years. So this is what we're thinking in our head. That's a fact we know, that if I have 350,000 to start with, when it doubles to 700,000, it's going to take 25 years for this problem because they said the doubling time was 25 years. So why don't I use that to my advantage and try to go find r? There's different ways to find it, but that might be the most logical way to think through it. So 700,000 occurs if 25 years pass. So basically, this was my time, this is my population at that time. 25 years later, I'm going to end up with 700,000. Now I can go ahead and quickly solve that and find my r value. Again, I'm going through this spiel because they did not give me the relative growth rate in this problem. I can go ahead and take ln of both sides. That's going to give me ln of 2 equals 25r, and voila, we have the relative growth rate, which they had not given us to begin with. And if I approximate that and punch that in, it's going to be about 0.02773. I'm going to carry 5 digits just so I have accuracy once I'm ready to graph that. So even though I did not have the relative growth rate, I was able to find it and give a final model. N of t is 350,000, e to the 0.02773. So part A, let's not forget the t. Part A was how the population grows in terms of its doubling time. And part B is how the population grows in terms of its relative growth rate. So how it's growing every moment. Now it says sketch a graph of the population. Well, both of these graphs are going to be the same because one of them is in terms of its doubling time The other one is in terms of its relative growth rate. So graphing it in part C, I'm going to go put the first one in. Let's pull up our graph. I'm going to put the first one in blue, and I'm going to do the second one in red. And because both of them describe the exact same population, but in terms of different growth rates, both of those graphs you'll notice will be identical. So I'm going to go put, let me put it in thousands. So I'm going to put just 350 in thousands. I'm going to put this in 350 raised to the t divided by 25, and in thousands for this one I'm going to put 350 e to the 0.02773t. So again, I'm going to have my y-axis in thousands. So 350 means 350 thousandths. And both of them are growth, so a sketch would be like that, but what I want to emphasize is that both of them will give me the exact same graph. So I could have different models for the same population. They look different, yet they're the same population and they describe the same thing. So let's go put the one in blue. That's 350,000, but I'm putting it as just 350 because my y-axis is already in thousands. 2 raised to the x or t divided by 25 is my first graph. And I'm going to go to a window that I know will work nicely to give a good visual of this graph. So I'm going to go to window between 0 and I guess 100. And then I'll go between 0 and like 2500. And again, I played around with it before I did this to see what a good window would be. And that works out pretty good. I'm going to push graph. And there's my growth in terms of its doubling time. But now if I go put the other one in terms of its relative growth, which is 350,000 e to the 0.02773x. Now I'm putting in terms of its relative growth. Watch what happens. If I push graph, it's exactly the same thing. The red one lies exactly on top of the blue one. So even though my models look different, both of them describe the same population. So part C, we have the sketch. Part D says, estimate how long it takes for the population, I guess, to reach 2 million. So for part D, if you want, it doesn't matter which one you use, whether you use the red one or the blue one, because they both describe the same population. So maybe I'll just use the red one with the E involved. So I have E 0.02773t, and we want to know when the population will reach 2 million. It's going to be 350,000 e to the 0.02773t. And we can go ahead and divide both sides by 350,000 and solve that. So we've got E 0.02773t. These are gone. This is gone. So I have 200 over 35. I can punch that in and approximate, or just carry it all the way into my TI. That way I don't have round off error. I'm going to take ln of both sides. Since I'm punching it in, I'm not even reducing it. The calculator will do that for me anyway. So I have 0.02773t. Divide both sides by 0.02773. And let's see when the population will reach 2 million. So I'm just going to go punch that in, and you guys do it along with me. Divided by 0.02773, and I'm getting something about approximately 63. The unit was in years, right? In approximately 63 years, the population is going to be 2 million. And if you want, we could even go look at this on our TI. So I'm going to go to the TI, and I'm only going to use, I don't know, since I did the algebra and the math for 63 years with the red function, let me clear that and use the blue function to get the same answer with the TI. So there's the graph for it. But I want the population to reach 2 million, and 2 million in thousands. So continued here, 2 million is, I guess, 2,000 thousands, right? If I want to put it into my TI, since my scale was in thousands, so 2 million, if I want to take out 1,000 from it to adjust my scale on my TI the way I put it, because I didn't want to put the whole million in, that's going to be 2,000. So I'm going to go put in Y2, 2,000, and see when my population reaches 2 million. Again, I repeat, since my Y scale on my TI, I chose to have it in thousands. 2 million will be equivalent to 2,000. And if I look at the graph, it'll tell me that at a certain point I will reach 2 million. So I'm going to use second, trace, and I'm going to use 5 for intersect. Is that the first curve? I'm going to say yes. Is that the second curve? I'm going to say yes. And then it says, should I guess? I say yes, and notice what it gives me, what I got algebraically, about 62.86, or about 63 years later, the population will reach 2 million. So you can do it algebraically and then confirm your answer graphically. So let's stop there, and we will look at the next example in the next video.